Okay, Assalamualaikum and a very good day to our beloved lecturer, Dr. Hamdan. So this is our presentation about Integrated Design Project, ECH 3705, Plant Design Presentation, Production of Ethylene from Natural Gas. So we are from Argonne Laboratory Sdn, which is Group 9. So before we start, I would like to introduce ourselves. So my name is Muhammad Aliff Ikhmal bin Zulkafli. My matrix number 198978.
Hello, my name is Divyashini Mohan with matrix number 198900.
My name is binti Muhammad Arshad. My matrix number is 198776.
We start with the introduction. So our company, Argonne Laboratory Sdn, has been set up in Malaysia and mainly focused in the production of ethylene from natural gas due to the wide accessibility to the natural gas. Generally, our company has been assigned to accomplish the production of ethylene from natural gas with using Oxidative Coupling Method, which is OCM. From the targeted approach, our main mission to produce 99.9% of ethylene with maximum mass production. So to achieve the mission, the cycle stream has been developed to our plant to increase the mass production to higher quantity. So in this project, our company are also required to determine a design parameter for any of distillation column in our plant. So we decided to choose C2 splitter as our main unit operation. So next. So this is about the block flow diagram. So I will briefly explain about the flow. So for the air feed will come to the compressor 1 through the ASU compressor 2 cooler 1 and straight to the OCM reactor. For the natural gas feed goes from the compressor 3 to the heater and then faced with the air feed from the cooler 1 to the OCM reactor. And then it continuously through the cooler, absorber, CO2 removal, and goes to the distillation column, section which is the metanizer, C2 splitter, and condenser. So next. This is the process flow diagram, same as the block flow diagram before. So next.
So now let us move on to the process description and also comparison between the manual calculation using Excel and Aspen. So will be the compressor. So we compare the calculation between Excel and also Aspen Simulation Plus. From the both calculation, we found out that the temperature outlet for the calculation differs. This is because of the type of compressor that is used. In Excel, we use an isothermal compressor, hence we assume that the inlet and outlet temperature remains constant. However, in Aspen Plus simulation, we used an isentropic compressor. So isentropic compressor is an adiabatic compressor. Hence, the temperature changes in the outlet stream. And also, if we look, the mass flow rate is different for the Excel and also Aspen calculation. This is because the mass flow rate is converted from the mole flow rate with the molecular weight. The molecular weight used in the Excel depends on the journal. However, Aspen simulation has its own built-in function. So that leads to the difference in the mass flow rate. So now moving on to the second unit, which is the air separation unit. This unit is used to increase the purity of the oxygen. So if we look at the differences, the difference we can see is at the top stream. For the Excel, we have around 624. However, for Aspen simulation, we have around 622. This is due to the purity of the oxygen found in the top and also the bottom. In Excel calculation, we assume that there is no oxygen at the bottom stream. However, in Aspen simulation, there is a small amount of oxygen in the bottom stream, which leads to the difference in the mole flow rate of the oxygen. Now moving on to the third unit, which is the compressor. Again, this is used to increase the pressure from 5.26 bar to 11.9 bar. So the 11.9 bar is the required pressure for the reactor. Again, the isothermal compressor used in Excel causes the temperature to remain same. However, in Aspen simulation, the isentropic compressor causes the temperature change or the temperature to increase at the outlet stream. Again, the mass flow rate is due to the molecular weight used in the Excel and also Aspen simulation. Moving on to the fourth unit, which is heater or cooler. So two different temperature controlling unit is used in Excel and also Aspen simulation. So this depends on the type of the compressor used earlier. So in Excel, we use an isothermal compressor, hence the temperature of the inlet remains 25. So we need to use a heater to increase the temperature to 365.7 degrees Celsius. However, in Aspen, we have an inlet of around 400. Hence, we need to use a cooler to reduce the temperature to 365.7 degrees Celsius. Now, moving on to the next unit, which is the compressor. So the two compressors used earlier is for the oxygen stream. However, this compressor is used to increase the pressure of the natural gas stream. So the natural gas stream is increased from atmospheric pressure to 11.9 bar. And also, again, isentropic compressor in Aspen simulation causes the temperature to increase in the outlet stream. So now we are moving on to the sixth unit, which is the heater. So this heater is used to increase the temperature to 365.7 degrees Celsius, which is the reactor's temperature. In Excel calculation, it increases from 25. However, in Aspen simulation, it increases from 300 to 365. So the next unit is the most important unit in our plant, which is the reactor. So the reactor that we use is the oxidative coupling of methane reactor. So as I mentioned earlier, the mole flow rate differs for both the Excel and Aspen simulation is because the mole flow rate of the natural gas depends on the mole flow rate of the air. If we look back, the air flow rate for the Excel and Aspen simulation differs about 1.7 at the top stream because of the oxygen purity. So that leads to the difference in the mole flow rate for the Excel and Aspen simulation in the reactor. And also the mass flow rate is again due to the difference of molecular weight used in the Excel and also Aspen simulation. Excel, we refer journal, however, Aspen has its own built-in molecular weight.
So next is cooler. For both calculation, the temperature and pressure for inlet are the same, which is 600 Celsius, and the pressure is 11.9 bar. And for outlet stream, the temperature and pressure also the same, which is 40 Celsius and 11.9 bar. In Excel calculation, we assume that the oxygen was fully reacted with methane during the combustion process in oxygen reactor. So there was no oxygen composition in this cooler unit. This lead to slightly different value of mole and mass flow rate for both inlet and outlet. Next. So next is absorber. The function of this absorber is to remove the water from the stream. For the manual calculation, we assume that water was fully removed from the raw material stream. But for the Aspen calculation, we use 99.99% efficiency, as it is impossible to have 100% efficiency in real life equipment. Therefore, the value for mole and mass flow rate was slightly different between both calculation. Next is acid gas removal. The function of acid gas removal is to remove carbon dioxide gas from the mainstream. In the manual calculation, the flow for this process is a bit different from the Aspen calculation, because it has its own recycle stream in this unit. The function of the recycle stream is to recirculate the solvent that we use, which is monoethyl amine, MEA, while while in Aspen simulation, there is no information needed for it. Therefore, there was quite a lot of difference in value of mass and mole flow rate. Next.
Okay, for the 11 unit operation, which is demetanizer, based on the result obtained from both calculation, temperature inlet remains constant, which is 40 degrees Celsius. But for outlet stream, the temperature in Excel calculation slightly different compared to the Aspen simulation for top and the bottom stream. In Excel calculation, our group have decided to neglect the presence of water on oxygen since their mole flow rate very low. This decision leads to the marginal difference of mole and mass flow rate for both inlet and outlet stream. So next, the next is C2 splitter. As a comparison, Excel calculation consists of 5 C2 splitters in order to achieve the desired purity. But for the manual calculation, it has but for the Aspen calculation, it has only one. So it is slightly different in the temperature for the inlet. Same as this demetanizer, we have neglected some of the component, which is methane, nitrogen, carbon dioxide, water, oxygen, since their mole flow rate were very low. This decision leads to the slightly different of mole and mass flow rate for both inlet and outlet stream and the total mass. So next, the next one is the separator, which is involving purging stream. So if we can see that the temperature is very slightly different. In our design plan, the function of separator is to split up the inlet flow rate by dividing it based on desired split fraction. In this case, we are set up the split fraction into 0.5%. So it is also we neglected some of the component. For example, in this condition, ethylene, ethane, water, oxygen, and since because their mole flow rate were very low, this decision leads to the difference of mole flow rate effect to the mole fraction of each component. So next.
So the next thing will be the recycle stream. This is something new that we add into our plan in this integrated project. So what is a recycle stream? Recycle stream is where a portion of the outlet of a process unit is combined with the fresh feed and sent into the same unit again. So in our case, it is an OCM. And then we chose the demethanizer to be to add the recycle stream. It is because demethanizer removes a lot of methane, which is the key component and that can be used as the source of ethylene formation in our plant. The methane will be converted to ethane via oxidative coupling of methane, and the ethane will produce ethylene and hydrogen. So the recycle can be done directly by channeling the bottom stream to the reactor. However, several problems can arise. So some steps should be done in order to prevent accumulation in the reactor. So we done a purging. The purging is done where a portion of the recycle stream is removed to avoid accumulation of undesired material in the recycle stream. So the purging process was done in the separator, as mentioned earlier by Aliff Ikhmal. So only 50% of the stream from the demethanizer enters the reactor with a split fraction of 0.5 to avoid the accumulation in the reactor. So now let us move to the design parameter of the distillation column. So we are required to choose a distillation column that is found in our plant for the sizing of equipment. Hence, we choose a C2 splitter. So there are a lot of parameters that we design for the C2 splitter. So I'll just discuss some of the important parameters. So there are two streams in our C2 splitter, which is the distillate and also bottom. The feed, we have cold liquid feed. The distillate and bottom, we have liquid too. And we have ethylene with purity of 99.95% at the distillate, which is the yield or which is the product that we need, with a flow rate of 94.984 kilomole per hour. However, in the bottom stream, we have ethane mostly with purity of 94.592%. Then next, we move on to the mechanical design of the distillation column. So we have around 25 theoretical plate and the feed enters at the 20th feet. The tower height is about 9.241 meter, which is acceptable because it's still below than 30. The column diameter is 2.3 meters. The common column diameter is 2.5. And the overall plate efficiency is 50%, which is quite good. And the material that is used to make the plate is a stainless steel. The whole diameter found in the plate is about 5 millimeter, and we have around 16,080 holes in total. So this is the overall mechanical design or mechanical drawing of our distillation column. So mechanical drawing includes tower height, the number of holes, the hole diameter, the tray diameter, tray spacing, tray thickness, and many more.
Okay, this is for the costing analysis. We have four units, which is capital and equipment costing, operating costing, sales expenses, and research development, and cash flow analysis. Next. Okay, for the capital costing is the estimate calculation of all of the equipment needed for the first and second year of business, including all the tax, site costs, human resources, and many more. So in our calculation, we have included all the equipments needed. So the total is around 1 million, and we are calculating to the ISPL, which is isolated battery load, and inside battery low and outside battery low. So the total is around 5 million. And for the total investment required, we are calculated to the design engineering D&E, which is 20% from the SPL plus OSPL, the contingency, which is the so the total fixed capital cost and the estimate working capital cost. So the total investment required is around 8.6 million. So next, for the operating cost is expenses associated with the maintenance and administration of a business. So the total operating cost for a company includes the cost of goods sold, operating expenses, and as well as overhead expenses. Okay, this is all the equipment and their energy. With some of them use energy to work, and some of them use the electric current. So we have calculated and times with the tariff rate, which is 0.33 times with hours, 24 hours, and day 330 days for a year. And then we total up the natural gas, which is 5.7 trillion MEA, and for the total of the operating cost for the equipment, so the total up to 574 trillion. So next, this is the cash flow in for our company in 20 years. We are getting our first first revenue, which is the sale at 8 years. But in the following years, we get negative cash flow. For the cumulative cash flow, we have calculated the positive amount around 12 years. So next, this is the overall figure of the cash flow, which is for the cumulative cash flow. We can see that for the first and second year is the stable way, but in the third year it dropped down very low, but we can higher achieve at the 12th year to the stable amount of the cash flow. So next.
Next is health and safety analysis. Health and safety analysis divide into 4 components. First, safety data sheet (SDS). SDS includes information such as chemical and physical properties, environmental health hazard, protective measures, and safety precaution for handling and storing each of the chemicals. Second, major health and safety concern. This is mainly to protect the health of people that involved in this plant design. Third possible safety hazard for each equipment. Uh, each equipment has their own standard operating procedure (SOP) that has been fixed. Fourth aspect of process design that address one of these safety concerns. In this plant design, OCM is one of components that involve chemical reaction between oxygen and methane. This reaction may cause uncontrolled chemical reaction, uh, which can lead to explosion or flammable ignition. Therefore, we need cooler unit to lower the temperature from OCM to other components as it operates at high temperature. Next. The main objective of this design project is to produce ethylene using natural gas with a feed rate of 3,192.76 kmol per hour, which equivalent to 1 million ton per year. In this plant design, we have 9 equipment, uh, including OCM reactor, aspiration unit, compressor, acid gas remover, absorber, demethanizer, NC2 splitter, condenser, and heater. Besides, there is also a recycle stream in our plant design that recycle the top outlet of demethanizer back to the OCM reactor with the feed of 1 million ton per year. 94.9844 km per hour ethylene is produced with 99.95% of purity. And the cost price for raw material and catalyst is 574.835 ringgit per ton, and the average selling price is 5,342.48 ringgit per ton, and our target profit is 90,501,760.41 ringgit. Next, and there are some recommendations to maximize the production of ethylene and to increase the profit. First, we should use other catalyst which is more facile and efficient. Second, the nitrogen gas which is removed in the ASU can be used as the nitrogen blanket inside the vessel in order to prevent explosion between methane and oxygen. Next, another distillation column should be added in order to increase the purity of ethylene. And finally, the operating years was chosen to be 330 days per year to allow for slightly over a month total throughout the year for the maintenance operation. That's all from us. Thank you.